All right, this is the 2020 AZ Water Student Design Competition, Project 19131. I'm Glacier Kane.
I'm Odell Balboa.
I'm Michael Zhang.
I'm Xavier Plasencia.
And I'm Marcos Lee.
This is our design poster. For this video, as you'll see, we're gonna blow up each section as we go over it, so that way the viewer is given the opportunity to read it fully. We're gonna start with our problem description. So for the 2020 AZ Water Student Design Competition, the Kyron Water Reclamation Facility in Tempe, Arizona is planning on reopening in 2025, and we are tasked with redesigning the opening of this new facility. The facility was previously constructed in 1991, and in 2006 it was upgraded again to handle 14 million gallons per day of wastewater influent. In 2025, for the reopening that we are planning for in this project, we're going to handle an average of 4 million gallons per day influent. So that's a small step down from the 14 it was originally sized for. The main things we're looking at for our build design is we're aimed at minimizing cost for running the plant, and obviously the cost going into reopening the plant, redesigning the plant, and optimizing efficiency. So we want to get the best Class A+ effluent water that we can as cheaply as possible. And the Kyron Water Reclamation Facility also has a stretch goal of being carbon neutral in 15 to 20 years. So we're looking at being as environmentally sustainable as possible.
Why are wastewater treatment and reclamation facilities so important? Fresh water that is primed for human consumption only makes up about 3% of the water available on Earth. That means that the majority of the water that we have access to requires recycling. A lot of processes and equipment that we utilize in various processes leave the little water that we do have available contaminated with harmful byproducts, so that has to be processed so those byproducts can be removed, right? And that is accomplished in a 3-step process, right? There's a primary, secondary, and tertiary phase. The primary phase looks to remove most of the dissolved solids and suspended solids within the wastewater, right? And we're doing that through physical filtration methods such as screening and the like. And then we move on to our secondary phase, which is the start of removing organic matter, right? Bacteria and things like that through the anoxic chamber and the aeration basin that we have in our process. And then our tertiary phase is bringing our water up to the A+ effluent quality standards set by the state of Arizona. So we're doing that through utilizing ultraviolet light through a process called UV disinfection.
In order to simulate the process we were designing, we had to use BioWin. And what BioWin takes is the influent data, or the data that we were given by Kyron Water Reclamation Project, and we changed the data in order to be able to put it into BioWin. We then had to add all the different processes that occur in the plant, with the exception of UV and the blowers, which BioWin can't simulate. So we had to put in all the pumps, which then first we have the influent pumps, which then lead to the clarifier and grit removal, then to the equalization tank, splitting it into one stream that gets sent to the 91st, which is the grit that the grit removal tank removes. After that, it gets moved into the equalization pumps that send it to the aeration tank, which has an anoxic zone and aerobic zones. The aeration basin uses pre-denatrification, which means it has 2 recycle streams, one inside of it taking aerobic effluent and sending it back into the anoxic zone in order to treat nitrogen better. After it's treated there, it's sent to the membrane. The membrane then sends the treated water without any solids in it, which then sends it to the places that need the water. The solids gets turned into sludge and gets sent into the recycle pumps and to 91st from a ratio that was calculated using the data that was given to us by Kyrene.
So next is the implementation process. And I'm just going to run through the process from start to finish. And so first, what we decided to do for the solids removal section is keep the original screening and vortex chamber, since it was a problem to replace them, or it caused a problem to replace them, and it worked fine in the original operation or design. Next was the aeration basin, where we decided to replace the age diffusers, or recommended to replace the diffusers, as well as decreasing the amount of aeration basins to 4. Next was the aeration system, which was the blowers and the pumps into the aeration basin. So for that, we decided to add variable drive frequency blowers, which modified and adjusted the amount of aeration or air needed for the aeration basin, depending on the need. Next was the membrane filtration, where we decided to use membranes with a surface area of 300 square feet and reducing the trains to 4, as well as reducing the amount of cassettes in each train to 8. And then lastly was the UV disinfection, where we decided to keep that the same as well, which was 7 chambers or 7 reactors.
Here we have our results. The graph shown below is a comparison between the permit required ranges and what we got out of BioWind, the modeling software we use to simulate our process. In the gray, you can see in the 4 left columns, they are the permit threshold requirements for certain components of the system. We chose the most prominent ones, which are the total suspended solids, the biological oxygen demand, and ammonia, as well as total nitrogen, and the effluent, which is the wastewater coming out of the plant that is produced, its pH. For the economics of this project, the total bare module investment, which is the amount invested towards equipment and the construction of that and installation, it will be $5.38 million. The annual cost of treatment, which is the operating cost of the plant, would be $6.3 million per year. And then the total direct permanent investment is $6.5 million, which is just the amount of money invested into the plant that won't be gotten back after the initial startup in 2025. Then we have a total capital investment of $8.8 million. That's just the total amount of money invested. And of that, $7.66 million of it will be depreciable. So that includes things such as equipment, which devalues over time.
So that concludes the outline of our 2020 AZ Water Student Design Competition. We thank you for your time and we hope you stay safe and healthy.